I say olefination, I'm just gonna give the right. So we're just talking about making alkenes, right? And there are lots of different ways to do this. I'm sure you can remember from um, organic two, we talked about one of them. If you took organic two from me, we talked about one of those olefination reactions, which was the Vidic reaction. That was a while back. Um, so we're gonna talk about the Vidic in great detail. And let me just give you. So we're gonna talk about Peterson olefination. We're gonna talk about the Vidic, Julia coupling. The Horner-Emmons, Horner-Emmons reaction, and and then we're going to also talk about some metal mediated, some transition metal catalyzed olefinations. We'll talk about that. Uh, and then we're going to talk about conversions of alkynes. So taking triple bonds and turning them into double bonds, either through uh, hydroboration type technology or hydrozirconation. Right, so we're gonna that's just basically an overview of this section. This is a big section, but we're gonna get through it. And I have notes and handouts already on Blackboard, but I'll send an announcement out to point you to where to find everything. Let me see. Yeah, so we're gonna let's start out uh, talking about the conversion of carbonyls into olefins. Right, so we'll talk about that, and then we're going to talk about the Peterson olefination, which is an elimination type reaction. Right, so uh, if you when you think about um, synthesis of alkenes, sorry about that. Right, one of the ways that to think about that is to do a dehydration. Right, and many times you can do a dehydration from a alcohol, or you can start with a carbonyl and then eliminate either water or some other leaving group. But all of these are going to involve an elimination. So let's say I have a carbonyl. I'm going to label that R1, and then I react that with some nucleophile. Let me get this together. So I have some nucleophile with the R2 group on it, right? And when I react those two together, I'm going to get this intermediate. Right, and depending on the nature of Z, and depending on the conditions, this the elimination is going to take place in one or two ways, right? So let's think about the first elimination pathway. So the conditions are going to determine that how the elimination takes place. Right. So in one sense, you can think about the intermediate, which I'm just gonna redraw it. The intermediate here, right, where if oxygen donated into Z, right, and you lost, like so, this would give you a, and again, this is important about these olefinations or these alkene synthesis reactions, because the alkene stereochemistry is really what you're after, right? You want to have a method where you can make either uh, a cis alkene or a trans alkene, right? So in this case, if this eliminates like so, and I'm gonna explain what using a Fisher projection, I'll explain why this is important. But if this is the case, right, this is going to give me a cis alkene, all right, because R1 and R2 are on the same side. If we think about this in terms of the transition state, and we think about it in terms of a Newman projection, I said Fisher earlier, I'm sorry. Think about it in terms of a Newman projection, right, where the oxygen is here and R1 is here, and this is all in the eclipsed. And then here's Z here. Let me redraw that. Right? Z and O are in what we call a syn periplanar conformation. Right? Syn periplanar. What that means is that they're on opposite side, the same side of the same plane. Right? Syn periplanar. When this is the case for a system like this, then you end up with these cis type alkenes, right? So how do we generate the trans alkene? Like what can we do to get to the trans alkene? Obviously, if you create a situation where Z and O are on opposite sides, then that's going to give you the opposite stereochemistry, right? So when we do that, again, it's all based on the condition. So if I start with that same intermediate, I'm just going to copy it from up here. I start with the same intermediate, right? But then I treat this with a proton source, right? Basically converting the OH, I'm sorry, the oxygen into water, which is a different type of leaving group, all right? Uh, I'll end up here. Of course, that has a positive charge. And then Now Z is here, and then R2 is here. Now though, the oxygen can't donate directly into Z, and then Z can't donate directly into oxygen. And so what ends up happening is this bond rotates so that Z is now on the opposite side of the leaving group. So I end up with a intermediate that looks like this. So now I'm here. This is Z, and now this is R2, right? And then when that eliminates, that's going to give me a trans alkene. Right? But I'm able to do that based on the conditions. If I get Z and R opposite to one another, which I did in this case by adding in, doing it under acidic conditions, then I'm able to eliminate and get the trans alkene. And again, if you look at the transition state for this, if you look at the intermediate right here and draw it, well, not that one, sorry, the intermediate here, and draw it as a Fisher projection, Newman projection. Keep saying Fisher projection. What you'll see is that now your leaving group and Z are on opposite sides to one another. Let me move that down so it's not on that line when I post it to Blackboard. All right. So now the leaving group, which is here, and then Z, we say that they are now in an anti-periplanar relationship. Right. So it's anti-periplanar instead of saying periplanar, and that determines your alkene stereochemistry. If the reaction takes place through an anti-periplanar conformation, then you're going to have the trans product. If it's syn periplanar, then you get the cis product. All right. So this is one method of alkene formation where you take some type of nucleophile that's substituted with, in this case, a Z group can be silicon or something like that. Or in the case of the Vidic, it would be phosphorus. But you take that and you react it with a carbonyl, and depending on the conformation that it goes through, that's going to determine the stereochemistry. All right, so we're gonna take what we know from here, and we're gonna use it to help to understand the Peterson olefination, which is a type of olefination that uses a system similar to this, where Z is a silicon group. All right, any questions so far? All right, I got room. I'm just gonna draw a line right here and here. Right, so with the Peterson olefination, what I'm taking is like an alpha silyl alcohol, and And depending on whether I do it under basic conditions or acidic conditions, that's going to determine if I'm able to get a cis or trans alkene, right? So let me show you the starting material, which looks like this. So you have a silicon, a trimethylsilyl group here. And then depending on whether I do this under basic conditions or acidic conditions, is going to, again, determine the stereochemistry of the alkene. So if I treat this with potassium hydride and do it in DMSO as the solvent, right, what you would expect is exactly what happens. Under basic conditions, you get a cis alkene, right? And then under acidic conditions, using acetic acid, let me zoom in a little bit more, sorry about that. So acetic acid and then sodium acetate, right? You get the trans alkene. All right. And so when you think about the base catalyzed version of this reaction, where potassium hydride acts as the base, right? So what potassium hydride does is proton transfer with your alcohol. Okay, let me just write that. Those as methyls. Right, and you can see now this is set up for uh, oxygen to donate into silicon, right? Just like so. Boom, here, here, and then you get your elimination, right? One of the things that drives this reaction is that silicon oxygen bond formation. That is a really silicon and oxygen. That's a really strong bond. So you're giving off a lot of energy, highly exothermic, when you make that bond. So it's a good thing. All right. Um, Another thing to think about is where oxygen is donating those electrons. And if you know anything about silicon, you know that number one, sorry about that. Silicon can be hypervalent. It can go hypervalent. So it can form 4, 5, or 6 bonds because it has empty d orbitals. So oxygen here is donating into the empty d orbitals on silicon. Right, so it's donating into empty d orbitals on silicon, right? And that's how that's able to happen. All right. And then if we think about the stereochemistry, then obviously this should give us the cis alkene. Right? If we do this under acidic conditions, then we should expect something to happen, right? Something different. We should expect Right? So we should expect the trans, and that's exactly what we get. If we do this under acidic conditions, we have a that's acid catalyzed process and treat it with uh, again acetic acid or some other acid, right? What you're gonna have, I'm gonna draw it here first. So I'm gonna treat that with H plus and convert the oxygen into a hydronium, and then you'll have your bond rotation, right? And when that happens, right, it'll get the hydronium and the silicon in an anti-periplanar conformation. Like so, right? Once that bond rotation happens, let me fix that up. That's kind of sloppy, right? And then what facilitates this is the addition of the conjugate base from your acetic acid. So here, so this is the conjugate base of acetic acid, right? Because the proton from acetic acid went to oxygen here, right? So you have one uh, conjugate at. Did I say? Let me fix that. Right, so that's the conjugate base of acetic acid. That's going to come in and attack silicon and facilitate your elimination. So that's going to cause this bond here to break, the carbon silicon bond, and also the loss of water, right? And you can imagine, depending on the substitution here, right, this could be an E2 type elimination or E1 type elimination, depending on how that carbon is substituted. All right, everybody remember those E2 and E1? Anybody not remember that?
Can you repeat that really quick?
Say that one more time.
I don't remember the E2.
Yeah, yeah. So this is an E2 type elimination because it's all simultaneous, right? It's all happening at the same time. Even though there's no external base removing a proton, the mechanism is concerted like an E2. So that's why I say it's an E2 type. But if this carbon right here that I have highlighted was more substituted, then you could imagine oxygen leaving first, right? And leaving a carbocation behind. And then it would be more like an E1 type. But in this case, it's not. All right. Uh, so one of the things that happens here in order to get, in order for this to happen, right? If you notice here, we have to break uh, this bond right here, right? And we also have to break this bond, and we need to make this bond. Let me change the color on that, right? And so if you notice with this being anti-periplanar, I want to show you something. So the sigma bond right here, I'm gonna start with the bond on silicon. The C sigma bond, which looks something like that, has the overlap with the sigma star of the CO bond adjacent to it, right? So the sigma star is going to look like this, where I have a, we'll change the color on it, where I have a lobe here and then a lobe here, right? Because sigma star is anti-bonding. So in order to make the pi bond and break the carbon oxygen bond, you have uh, carbon silicon sigma, and then that's going to overlap with the CO sigma star. What you'll find out is that anytime you break a bond, normally by donating electrons and not just spontaneous bond cleavage or some other type of cleavage. When you break a bond, you normally are donating into the sigma star orbital of that sigma bond, right? And that's what causes that bond to cleave. Because again, the sigma star is empty. It's intended to be empty, right? If you look at a orbital diagram uh, for any sigma bond, you have sigma, which has your electrons in it, and then sigma star, which is empty, right? So you're gonna, if you are donating into sigma star, then that's gonna cause a sigma bond to be cleaved. All right. So that's the Peterson olefination, and you get the trans alkene under acidic conditions. Plus, you get. Let me draw the other side product. Plus, you get this. Uh, right. The conjugate base picks up the silicon group. So you have the TMS connected to that conjugate base, right? Um, and this is again these beta hydroxysilanes, which is uh, the base substrate or the model substrate for Peterson olefination. You take a beta hydroxysilane and then you either treat it with a base or acid, and you can get out an alkene. All right. Any questions about that? All right. So let's look at the Vidic reaction. We're gonna talk about that, and I want to talk about uh, a little bit of controversy with the Vidic, um, based on some mechanistic evidence that shows that one of the initial thoughts about the Vidic is kind of, well, it's wrong, and there's another way to think about it. So let's do that. Let's talk about the Vidic, and then we're gonna come back and talk about the different alkene conformations. I don't want to do that now. I'll do it after we talk about the Vidic. And then we'll talk about alkene conformations, A1,3 interactions, and then A1,2 interactions. So we'll talk about that after the Vidic. But let's look at the Vidic reaction. Uh-oh, we got a lag. All right, and you've seen this reaction before, right? Uh, in undergrad, you take triphenylphosphine and you take alkyl halide, like I'm just going to start with that, and then you take a base, Well, let me not do that. You take a carbonyl, either aldehyde or a ketone, and then you react this in the presence of a base like KOH or some other strong base. And then what you end up with is a alkene, right? And if you remember from um, organic 2, when you took it, this proceeds through a or an illet. Anybody remember that? So the illet is basically the product of the triphenylphosphine and the alkyl halide and the base, right? So let me show you what happens there, and then we're going to talk about the reaction itself. So you make your illet by triphenylphosphine attacking your alkyl halide, like so, at the carbon. So you do a substitution, right? And then you end up with this, right? This is positive, and then the negatively charged bromine just is kind of just hanging out like a salt. And then after that, you treat that with that base, and that's going to remove one of these protons here, right? So what you end up with is that's negative, that's positive. This is your illet. That's going to get cut off, right? And so that's what does the reaction with your aldehyde, right? That's what does the reaction with your carbonyl, right? So if I took if I started with an illet like this, right, I could also write it this way. Either way is fine. Both of them represent the same thing. You can write it with the pair of electrons shown, or you can write it with the double bond between carbon and phosphorus. It doesn't matter. It's still gonna have the same uh, reaction. So if I took this illet, right, and I react it with an aldehyde, right, this is going to attack here like so. So you get a nucleophilic attack and addition to the aldehyde. And then from that, you're going to get an intermediate, kind of similar to what we just saw, where we have the so now oxygen is negative, and then we have there's a there's a big lag between my writing. So once that carbon attacks, you're going to get this intermediate, which has traditionally been known as a beta-ene. But the more recent research has shown that the beta-ene doesn't exist. Right? It's a different type. It happens a different way. And we're going to talk about that in a second. So the beta-ene is here, and then what was proposed is that it collapses, right? So you make this PO sigma bond because the bond between phosphorus and oxygen is a really strong bond. So you make a PO sigma bond first, and then from that, this collapses like so, and then you end up with your alkene. And then the plus phosphine oxide, which is basically the driving force for the reaction. The phosphine oxide is you get a PO double bond, and that is a really strong bond. So it's you give off a lot of energy by forming that, and so that reaction that's kind of the driving force for the reaction. All right. So let's talk for a second about the other proposal, right? Because the beta ene again, and this is some info. This is some. This was done by Peter Whiff. And so let me show you what they propose, and I have the reference for this too. Right. So what Whiff is proposing is that the beta ene doesn't even exist. He's proposing something totally different, and he's proposing that the way the illet and the aldehyde interact is through like a six-member kind of a puckered transition state, right? And so there is a paper that I want you to grab. I think it's already on Blackboard. There's a paper by Vidic, and in that paper he discusses why he believes the beta E doesn't exist, right? And he does so through a series of mechanistic experiments, right? So we're gonna I'll make sure that's uploaded. I think it already is. Um, but what he's proposing is that the beta E doesn't exist, but and the reason is that uh, he doesn't see evidence for that illet, that Zwitterion illet in the mechanism. And so what he's proposing is instead of the beta E, he's proposing like a what he calls a force center transition state, which I'm gonna show you now. All right. So and it's like a pucker type transition state. So if he takes let me see what he took, what he started with. Okay, he started with this. Let me zoom on that so I can write it. So it's this, and then plus, here's my aldehyde. So if you notice, like first, he's not even proposing like attack followed by cyclization. What he's proposing is like direct cyclization from the from the illet, not the zwitterion where the carbon is negative and the phosphorus is positive, but directly from the illet, right? So from here, it's basically two pathways that this can follow, right? So one pathway is here, And again, he's proposing a chair type transition state. And let me bold this line out because this line, sorry about that. Let's draw it again. So this is on top. Trying to darken it up so you can see that it's up on top of the other bond behind it, right? And then so you have that, and then move this arrow. Right, so that's one proposed transition state where you don't go through the beta-ene, you go through basically a direct addition, right? And that's how that's the confirmation that the aldehyde and the ylate adopt in order to overlap and give you uh, in order to overlap and give you that oxaphosphatem intermediate, which I didn't give you the name for above, but let me go back and label that. Right, so this intermediate right here that's believed to collapse and give you the alkene is called an oxaphosphatem. Right, so from this transition state right here, that's going to give you this oxaphosphatem. Zoom in so I can get my bonds looking right. And that's R1 from the aldehyde. And so this confirmation right here would give you the cis alkene. Right? Let me shrink this a little if I can. Right? So he's proposing that the beta-ene doesn't exist. You get a planar transition state, right? With one transition state, which I have drawn here, giving you uh, the cis alkene, and then the other, which I'm going to cheat and copy this. So give me 1 second, and then the other transition state is going to look like this. So I'm going to label this as TS1, and that'll give you the cis alkene, and then in TS2, right? The difference in TS1 and TS2 is the positioning of the R group and the hydrogen from your ylate, right? So in TS1, you can see that R is pointed up, and then the hydrogen is equatorial right here, and the R group is axial. But in TS2, it's the opposite. So this hydrogen now is axial, and then R is equatorial. And so from here, this is going to give you this oxaphosphatem that looks like this. Right now, R is here, and R1 is here. And that eventually leads us to the trans alkene. All right, and so he's proposing in that this transition state is less stable because of the steric interference that happens here between R and R1. So this is, I'm going to write it down here that this is disfavor. So that's disfavored relative to TS2. All right. All right. So we're gonna pick this up on Monday. I'll post this document from WIF so you can read over it, and then on Monday we're gonna finish this discussion about these transition states and how this information applies to other types of islets, because you can have stabilized and non-stabilized islets, and that changes everything, right? The stabilized, if the islet is stabilized, meaning if it has an electron withdrawing group on it, then the outcome is gonna be different, right? For different types of substrates. So we're gonna pick this up on Wednesday. All right. Any questions before we log off? It should be TS1. My bad.
No questions at this moment.
All right.
But you did say this is going to be uploaded, correct?
Oh, yeah, absolutely.
Okay. Okay.
All right. Yes, Jen. I'm in class, Jen.